And the next talk will be given by Luca Abergo from the Politecnico di Milano, and he's going to talk about the design optimization. Luca, will you take over?
Can you hear me?
Yeah, we can hear you. We cannot see you.
Okay.
We won't be able to see Luca because he's on Linux.
Okay. So we can hear you. Go ahead.
Okay, perfect. Good morning to everyone. Thank you for being here. It's an honor to be at this. We're going to talk about automatic shape optimization based on computational fluid dynamics. Can I control the slides? Okay. We want to automatically improve the aero performance of a generic lifting surface. There is a specific category between the lifting surface, which is not well treated in literature, since many optimization software fails to optimize them, and they are the non-planar wings. Most of the time, the optimization fails due to an issue during the mesh deformation process. In SU2 and in many other software, the method most commonly used is a physical analogy based called ELA, which is based on treating the mesh as a solid and solve like a finite element problem where we impose as boundary condition the movement of the surface that we want to deform. Instead, in our work, we decided to introduce a new method called RBF, which is an interpolation method. With this new method, we are able to handle more complex geometry and improve the quality of the mesh after the deformation. So we start from a solid that we want to modify. We select an objective function that we want to reduce, usually the CD coefficient. We use a technique called freeform deformation for describing the body mathematically, and the vertices of the box where we introduce the body are our design variables. We use the discrete adjoint to compute the surface sensitivity. In SU2, the discrete adjoint, we use a technique called AD, automatic differentiation, which differentiates also the routine for deforming the mesh. So the surface sensitivity is going to change if we change the method used for deforming the mesh. So the point of updating the grid, it is essential for the final result. Next slide. Okay. So RPF, it is an interpolation method. We know that the direct movement of the surface nodes, since we computed it using a discrete adjoint, we want the displacement of all the nodes. We use a technique where we sum some basis function, which value is proportional to the distance of one node of a mesh to the node where we exactly impose the movement, multiplied for some scalar weight. We need to compute the scalar weight, and we generate two linear systems. One for computing the displacement of the surface, and one for computing the displacement of all the other nodes of the grid, which are inside the flowed volume. RBF, usually it is computationally expensive. This is why it's not always used in optimization, but in Politecnico, we introduced two methods for reducing the computational cost and make it more efficient. The first one is an integrity algorithm. We are not going to impose the exact movement on all the nodes of the surface, but we're going to select some of them in an iterative way with the target of reducing the interpolation error introduced. The second one is used to reduce the dimension of the second linear system, the one related to the volumetric grid. So we are not going to shift all the nodes of the grid, but only the ones that are inside the range that we dynamically choose around the body, and it is proportional to the maximum displacement that we want to apply. We compared the old framework composed by the discrete adjoint and DELA for deforming the mesh with the new one, which is composed by the discrete adjoint for computing the surface sensitivity with RBF. And we tested it on some. I'm not able to change the slide now. I don't know why. Okay. We tested it on some cases The first one is the NACA 0012 in transonic condition. We want to minimize the drag, keeping it the angle of attack, the lift, the chord, and the maximum thickness. We need to select the number of design variables. If we use too few, we are not going to properly describe the body. If we use too many, the optimization problem becomes too stiff. Can you change slide, please? Okay, so here on the left, you can see the old framework in red, and it is reported the final value of drag of optimization, and in blue, the new framework. For both the methods, the best result is obtained for 16 design variables. On the right image, you can see how the CD is changing during the optimization. With RBF, just after 80 design loops, we obtained a strong reduction of the CD, more than 50%. Instead, with ELA, we need more iteration, and we obtain a less strong reduction of the CD. Next slide. This is due to the fact that we use two different mesh deformation techniques. So we have computed two different surface sensitivity, and we have moved in two different directions inside the design space. The NACA 0012 is pretty interesting because it has many local minima inside the design space, and we have found two not comparable shape of the airfoil at the end, and the shock it is positioned at two different stations of the core, generating a completely different CP distribution. And this is why we have a strong difference in the final value of the objective function. Next slide. Thank you. The first 3D case is the CRM wing, which is proposed by AAA Abergo research group. We want to minimize the drag, keeping fit the lift, but also the volume, and we impose many geometrical constraints like 50 section of the wing cannot change the maximum thickness, and also the root cannot completely change. This time we did not explore the number of design variables, since literature says that the best result is obtained for 128 of them. We monitored the CP plot at 5 stations. Next slide. And what we obtained also this time is a stronger reduction of the CD with RBF of almost 8 drag counts. We paid in terms of torque moment, which is increased, and we are not perfectly preserving the volume, probably due to the fact that we are introducing an interpolation error, which is intrinsic of RBF, but also the old framework does not perfectly preserve the volume. And in the next slide, we can see how the shape is changing at 2 sections, and the CP plot is way different from the starting one. The final test case, it is a 3D non-planar wing. We decided to use, next slide please, sorry. We decided to use an on-era with a winglet attached. This problem was already used inside another project called Onerone, which used SU2, but it was solved only Euler equation, and they generated a new mesh at each iteration. This time, we solved the Radial equation with Spalart-Lamar's model as turbulence model, and we updated the grid at each iteration. We want to minimize the trick, keeping fixed the volume and the lift as before. We are in transonic condition. And next slide. The key point is this optimization was possible only with RBF. This is why are not reported the results with the old framework, since just after one deformation of the mesh, the following run simulation was not able to converge, since the quality of the mesh was too much deteriorated. We obtained a strong reduction of the CD of almost 20 drag counts using 2 FFPD boxes, one for the planar one and one for the vertical one. You can see at naked eyes that the shape is changing, and the volume is perfectly preserved this time. During the deformation process, you can change slide, it's the last one. Okay, here you can see the shape of the airfoil changing and the CP distribution, but most important is the last slide. Okay, we recorded the memory allocation during the deformation process of the non-planar wing after just one step of the design loop. We did it with the old framework and with new one. ELA required 15 gigabytes of RAM. Instead, RBF only 3.7 and took half of the time. And it way better preserved the mesh, the quality of the mesh, the orthogonality of the mesh. This is why we were able to make the optimization converge instead of stopping it after just a few iterations. So collecting what we said up to now, last slide, please. The design space that we are able to explore is way limited by the mesh deformation technique that we are using. RBF is a good alternative because allows us to handle more complex geometry because it better preserves the quality of the mesh, and so we are able also to impose more important deformations. Also, it is computationally less expensive thanks to the new data reduction schemes that have been introduced in our department. Thanks you for the attention.
Luca? Yeah, okay. Luca, there was a question about is the RBF motion solver parallelized MPI, open MPI? Can you provide an estimation of the performance of the RBF motion solver, number of grid points, number of cores, and so forth?
Yes, of course. Okay, we were using some mesh, about 8 million of node, and yes, RBF it is parallelized using OpenMPI.
Okay, thank you very much. It was very